You know, for centuries, we've been asking what seems like a really simple question. What is light? Is it a stream of tiny particles? Or is it a wave rippling through space? Scientists basically went to war over this for generations, and for a while, it really seemed like the case was closed. But then, this one strange, totally baffling experiment came along that nobody could explain. An experiment that didn't just reopen the debate, but would end up completely shattering our whole understanding of reality itself. All right, so before we dive into the mystery, let's set the stage a little. By the time we get to the late 1800s, the scientific community felt, pretty smug. They were confident they had light all figured out. Yeah, this was a battle that went on for a while. You had Newton kicking things off, arguing for particles, but then Thomas Young's famous double slit experiment came along and showed light bending and interfering with itself, which is classic wave behavior. And the final nail in the particle coffin, or so it seemed, was James Clerk Maxwell. His equations were just beautiful, and they mathematically proved that light was an electromagnetic wave. So that was it. Case closed. Light is a wave, period. So while everyone's busy celebrating the big win for wave theory, there was this really peculiar experiment that was giving researchers headaches in labs all over the world. And it involved something incredibly simple, just shining light onto a piece of metal. They called it the photoelectric effect. The setup is actually super simple. You take a high-frequency light, like a UV ray, you shine it on a metal plate, and poof, electrons get kicked right off the surface. Now, if you're thinking like a 19th century physicist, this should be easy. The light wave carries energy, it hits an electron, gives it that energy, and the electron flies off. Simple, right? But when scientists looked closer, the results were anything but simple. They were just weird. See, the wave theory made a couple of predictions that just flat out didn't happen. First, if light is this continuous wave, then even a really faint low-frequency light should eventually build up enough energy to kick an electron out. You might have to wait a while, but it should happen. But it didn't. Below a certain frequency, absolutely nothing happened, ever. And second, if you make the light brighter, more intense, that wave should have more energy, right? So it should make the electrons fly out way faster, with more energy. But nope. All it did was knock more electrons out, and they all left at the exact same speed. It made absolutely no sense. So the entire physics world was stumped. The rules they had relied on for decades were failing, right in front of their eyes. This mystery needed a new hero, someone willing to think way outside the box. And his name was Albert Einstein. He decided to look at this whole problem from a completely different angle. Okay, so Einstein didn't just pull this out of thin air. He had a really important clue from the work of another physicist, Max Planck. Planck had recently come up with this wild idea that energy wasn't some smooth, continuous river. He said it could only be given or taken in these tiny individual packets. He called them quanta. And this is where Einstein has this incredible what-if moment. He takes Planck's idea and pushes it one giant step further. He asks, what if it's not just about how energy is absorbed? What if it's about how light travels? What if light itself isn't a continuous wave at all, but a stream of these tiny little energy bullets? And he gave these particles of light a name, photons. Each photon was a single particle-like packet of light, and it carried a very specific amount of energy that depended on its frequency. I mean, this wasn't just some small adjustment to the old theory. This was a complete revolution. To really get why this idea was so brilliant and how it just perfectly solves those two baffling puzzles, let's step away from the physics lab for a second and use a really simple analogy. All right, so picture this. There's a ball stuck high up in a tree. That's our electron, just kind of held in place inside the metal. And to knock it out, you're going to throw stones at it. Those stones, there are photons, our individual packets of light energy. Okay, let's tackle that first puzzle, the frequency problem. What if you only have tiny little pebbles? These are your low-frequency photons. You can stand there and throw thousands of them at that ball all day long, but not one of them has enough oomph on its own to knock the ball loose. But what if you throw just one single large, heavy stone? That's our high-frequency photon. It has enough energy in that single impact to knock the ball out instantly. And that's why you need a minimum frequency. The packet of energy has to be big enough. And this solves the intensity puzzle too. What happens if you just throw more stones at the same size? Well, that's just like making the light brighter. More intensity means more photons. You'll just knock out more balls, but each ball that gets knocked out flies away with the same speed as before. If you want to make a ball fly out faster with more kinetic energy, you don't need more stones. You need a bigger stone, a single photon with a higher frequency. And with that one simple, elegant idea, Einstein explained everything. The photoelectric effect suddenly made perfect sense. The impossible puzzles were solved. The evidence was just undeniable. Light, the thing we were all so sure was a wave, was behaving exactly like a particle.
But hold on. What about the double slit experiment? What about Maxwell's equations? All that evidence that proved light was a wave didn't just disappear. So what's the real story here? Is light a wave, or is it a particle? The answer would turn out to be way more profound and frankly weirder than anyone could have imagined.
The final answer is it's both. This is the incredible idea of wave-particle duality, and it's one of the absolute cornerstones of quantum mechanics. Light doesn't pick a side. It has a split personality. Sometimes it acts like a wave spreading out and creating interference patterns, and other times, like in the photoelectric effect, it acts like a particle, delivering its energy in these little punches. Which one is it? Well, its identity literally depends on how we decide to look at it. I mean, that's an idea that just completely breaks our everyday brains, right? It shatters our intuition about how things are supposed to work. And it leaves us with this really fascinating question. This one experiment showed that the very essence of light has this hidden dual nature. So you have to wonder, what else is out there, from the tiniest particles to the biggest things in the cosmos, that's hiding an identity we haven't even thought to look for yet?